Let's prove that the limit of the sequence as n goes to infinity is 0, and this is a sequence, so the inputs are whole positive numbers, in other words, natural numbers. So I'll take some positive epsilon, that's a real number, positive real number epsilon. That's the first thing, this classical epsilon, a Greek letter that represents some positive real number that can be a very tiny number. And then I will take n, which will be that natural number, because the inputs of a sequence is whole numbers, positive whole numbers, so they also order all the outputs of the sequence, their inputs, and then the sequence gives an output, so the 1, 2, 3, and we go higher and higher by natural numbers that labels every output, output of the sequence. And we say that beyond some input, capital Case n, the difference from the limit that we see here, that's the 0, alright, it's equal to a. Generally, limits are the limit convergence value of a sequence is labeled, for example, as capital A, in this case 0, so we'll use the letter A in a second, so let's have it there. But anyway, we'll see that after some capital letter n as an input to the sequence as a natural number, for every higher natural number than that, the difference from the actual value of the sequence from the limit that's we see a 0 here will be smaller than any possible real number epsilon. That's a positive one. So let's see, and also let's choose it that it's bigger than 1 over epsilon. So this choice will help us with the proof. All right, so we take some natural number, by the way, natural number capital N, such that it's bigger than 1 over epsilon. And it works because whatever real number, this is going to be a real number, whatever real number you take, the rule is you can always find a higher natural number than that for that particular chosen real number. All right, so now if we continue, well, we can have, also let's take some, let's sort of label here, we have some lowercase n that's in natural numbers. And for every n that's higher or equal than the uppercase n, we have that the difference between the supposed limit of the sequence and the sequence output at lowercase n value input of natural numbers, it's going to be smaller than some epsilon in positive real number, some very small real number epsilon. All right, the same epsilon here. And in this case, we're talking about 1 over n. So instead of 1 an, I put 1 over n, and the convergent value that it's supposed to converge to, we want to prove that it's converging to it, is 0. So let's see if that works out. And we don't have yet that it's more than epsilon, that's where we want to get. But it was useful, now we'll see, that the uppercase n, we set higher than 1 over epsilon. And this can be written as 1 over n. N is a natural number, so a positive integer, so the absolute value can be dropped, and it's equal to 1 over n. But that should be smaller or equal to 1 over capital Case n, because capital Case n, if we have natural numbers 1, 2, 3, until some capital Case n, and then we are talking about the lowercase n's that are higher than that, alright, at which, if our conversion value, that a is 0 this time, for example, that x-axis, well, the values were jumping, but suddenly after capital Case n, they're very small, smaller than any chosen epsilon. So after uppercase n, very high natural number, perhaps the lowercase n's that are higher even than that boundary level capital N, we'll have that this difference is more than epsilon, but we have to get there. And what we now at least know is that 1 over n, it's inverted because we have 1 over n. Well, those are high n's, lowercase n's are higher than uppercase n's. So if we do this fraction, then 1 over lowercase n is at least smaller or equal than 1 over capital Case n. And also from this choice stems another inequality that will basically finish up the proof. That is, if n is higher than 1 over epsilon, that means epsilon is higher than 1 over n. And that's useful because 1 over n is smaller than epsilon by that. And that's what we wanted to get. We wanted to see that the difference between the limit value, this a here, and some very high, beyond some level of natural numbers inputs, all the next will be very, very close to that limit value 0. So hereby it's proven. We got that epsilon is higher than 1 over n minus 0. Therefore, the sequence at n is going to infinity will converge to that value 0.